Hello everyone, let's get started. So in the previous lecture, we looked at discretization of unsteady convection equation using the central difference scheme, upwind difference scheme, and a Lax-Venn-Ross scheme, right, which was a fix for central difference scheme, isn't it? All right, so we looked at discretization and looked at the several properties associated and how the exact solution compares with the solutions obtained from these schemes. Okay. In addition, we also looked at couple of higher order schemes. One was the second order accurate upwind scheme, and the another one was the third order accurate upwind scheme, which we call it as the quick scheme, right? The quadratic upwind interpolation for convective kinetics, right? So that's what we looked at in the previous lecture. In today's lecture, we're going to look at implementing these higher order schemes. So how do we actually go about implementing them in a code? And we will then kind of switch gears and then look at discretization of convection diffusion equation on unstructured meshes, right? Because till now we only looked at how to discretize on essentially on structured Cartesian meshes only we have looked at. So today we're going to look at unstructured and essentially non-orthogonal meshes. Okay, so we're going to look at that in today's lecture, and depending on the time, we will also look at how can we actually extend these higher order schemes to unstructured meshes. Okay, that is something we have not. We have of course not done. Okay, so these are the kind of topics for today's discussion. So let us get started. So let us kind of review the convection schemes we have looked at in the last class. So essentially the convection schemes are if your flow rate on the east face is greater than or equal to 0, the way this is basically defined is if your UE is greater than or equal to 0, then your the flow rate on the east face would come out to be 0. Under such conditions, we have defined the upwind difference scheme as something that assigns the value of the face value, right, phi east, as the upwind value, that is phi p, right, because f is positive, so it is going in the positive x direction, so phi little e would be taken as phi p, right? That's what we have. And then if it is a central difference scheme, then the face value of phi would be taken as, of course, the arithmetic average of the east and the p cells. So we have phi e plus phi p by 2. All right. Then we have also looked at this second order upwind scheme in which the phi on the face, phi little e, is written as phi capital P plus phi e minus phi w by 4, right? So this was obtained using an approximation for the first derivative, right? The first derivative essentially is evaluated, the partial phi partial x is evaluated using a central second order accurate formula, right? Then you obtained essentially the Fromm scheme, and if you had used for expanding the first derivative using a backward difference, right? Backward difference formula, then you essentially obtained a scheme that is known as beam warming scheme, right? Basically you had the Taylor series expansion and phi p plus partial phi partial x. That is where we have used these two definitions for the first derivative. Okay, going on, extending the same concept, if you start including higher order terms, that is dou square phi by dou x square as well, and then use a central difference formula for both the first derivative and the second derivative, then the delta x that we have got cancelled, and then we essentially obtained something known as the quick scheme, where phi little e equals phi p plus phi east minus phi w by 4 plus phi east plus phi w minus 2 phi b by 8, right? These are basically the central difference formulae for the first and the second derivatives. Of course, in doing all this, we have assumed that we are essentially working with not only with a Cartesian mesh, but the mesh is also uniform. So it is probably a good idea for you to ponder on how do I extend, how to extend these schemes to non-uniform but let's say still Cartesian meshes. Okay, that is something I want you to kind of think about and see how do you extend these schemes. So what are the changes you have to make and things like that. All right, now okay, we looked at all these schemes, but do all these schemes look okay, or are there any issues that you see right away? yes, we do see some issues. If it is upwind scheme, we don't have any problem because phi E equals phi P. So this either phi P or phi capital E depending on the direction of the flow rate. So there is no problem because all the coefficients would come out to be positive. As we have seen in the context of the central difference scheme, there is a possibility for central difference scheme to have negative coefficients, and those can be avoided using the by maintaining the Self-Peclet number to be less than 2, right? That's what we have already discussed. Now, of course, if you are working with any of these higher order schemes, again you see that there are these neighboring coefficients which are the phi west and phi p here, which essentially carry a negative coefficient, right? So these negative coefficients are not good because essentially this is not good, and of course this is also not good because this is making the central value phi p to go to a smaller value, right? You have minus 1/4 here coefficient, which makes the central value ap to go down, right? Okay, so essentially these negative coefficients are not good because they do not satisfy Scarborough criteria, right? The moment you have these negative coefficients, your Scarborough criteria may not be satisfied. Essentially the diagonal dominance would not be respected, right? As a result, if we use an iterative scheme to solve for the solution, then we would run into trouble, right? Using an iterative scheme to obtain solution would cause issues because the Scarborough is not satisfied, right? As a result, we need to find a way of getting around this problem, okay, so that we can still satisfy Scarborough criteria, but we will not have any issues in converging the solution using some iterative scheme, okay. So we're going to look at one particular method, and after that I want you to think and see if there could be any other method that you can do this in a different way, okay. So let us get started. So implementation of higher order schemes. So we will see how do we get about this problem. So essentially, to satisfy Scarborough criteria, we use something known as a deferred correction approach, okay. So this was proposed essentially to make some of the kind of legacy codes that were originally written using the upwind difference solutions, okay. So in order to kind of make these work for high order schemes, a deferred correction approach is proposed. This also not only to make these codes work with small changes, but also to make any of these iterative solvers also to work, because then they will start satisfying this Scarborough criteria, okay. So essentially the method is same as what we have learned till now. This is basically a deferred correction approach in which we like the way we have done it for the source terms and the way we do it for any of the nonlinear terms. So what we do is we know that if we take a simple upwind scheme, that is basically the first order upwind difference scheme, this always satisfies Scarborough criteria because everything is positive coefficient, either it is going into the AP term or to the A and B terms, and you have no problem, okay, in obtaining the solution, okay. So what we do is essentially we take that point, and then if you consider the convective scheme, the discretized value is nothing but Fe times Phe, yeah, right? This is what you would get after discretization. So Fe times Phe, and if I assume that Fe is positive, Fe is greater than or equal to 0, then for a upwind difference scheme, what we do is if Fe is positive, then Fe Phe would translate into Fe Phe P, right? Essentially this Fe would go into the coefficient of AP, right? Or A east. If this was negative, this will go into A capital east, okay. Okay, now what about the higher order scheme? Let's say if you take some higher order scheme, which I would like to write it as HO, higher order scheme. So Fe Phe would become Fe times Phi higher order. Now Phi higher order is basically what? It is not just Phi P, but it is basically all this entire thing, right? Phi higher order is Phi P plus blah blah blah, or it is this thing or this thing, right? It's basically a big expression that contains not only Phi P but also contains several other neighboring values, which is given by the higher order scheme. Now we know that if I use directly this, it is not going to satisfy Scarborough because it's going to cause trouble with the coefficients. So as a result, what we do is we look at deferred correction approach. So what we do here is that we write Fe Phi HO, the higher order scheme, as we add and subtract the upwind difference component, that is FE-Phi-P. So I would add FE-Phi-P to FE-Phi higher order, and then I would subtract FE-Phi-P. Okay, so essentially this is same as what we have on the left hand side. Now what we do is that now in the deferred correction approach, we will evaluate everything that is there in this parenthesis, okay, using the previous iteration value. So we're going to put a star here for these two terms. Okay, so whatever we have here, this will be evaluated using the previous iteration values. Okay, so these are basically FE Phi H naught star minus FE Phi P star. Okay, now this is something that is not the same as what we have written in the previous step, but we understand that by writing it this way, we have now changed few things, right? Of course, what did we change? We have changed that excuse me. So we have changed that at convergence, what will happen here? At convergence, Phi P equals Phi P star. As a result, this term gets cancelled. Essentially, this term gets cancelled, right, with this term, and we kind of recover back our Phi H naught, right? That's what we would recover. And now what about Scarborough criteria? Now, because this term is written Fe as Fe Phi P, and these two terms are evaluated at the star level, that is the current iterate level, or known values, right, or the starred values, then where do these terms go, right? So if we have written it like this, Fe Phi H naught equals Fe Phi P plus Fe times, if I were to write this as Phi H naught star minus Phi P star as some delta Phi H naught star, okay, some difference between the higher order value and the Phi P value, essentially the upwind value, then where will these coefficients go? This coefficient will go into where? This will go into your AP, and where will this term go? Because this is star values, these will not go into AW, ANI bus, these will go into the B term. Okay. As a result, now your Scarborough is now satisfied, because it's basically similar to your upwind difference scheme, except that these are going into the source terms, right? So your Scarborough is now satisfied. As a result, for every iteration or the outer iteration that you have, your Scarborough is always satisfied and you have no problem, right? You can implement any higher order scheme in this particular way. All right, now let us take an example of the quick scheme and see how do we go about implementing it. So if we look at the quick scheme, what we have is Fe Phi E would read as Fe Phi quick equals Fe times Phi P plus, okay, so this particular thing, entire expression here is the Phi quick, right? That is what we have for Phi quick minus Phi P star. So essentially we have added Fe Phi P and subtracted it here, Fe times Phi P, and everything in the parentheses we are starting evaluating at star values. Of course, there could be a different way of doing this because there is already a Phi P star here, but I would like to follow with what we have written up here. Okay, so that means Fe Phi P equals Fe, so this basically equals Fe Phi P plus Fe times Phi P star now gets cancelled. So what you get is you get this remaining term. Okay, so essentially again now this entire thing would go into the B term, and this entire thing here would go into the AP term. Okay, so as a result, this Scarborough is now satisfied. Okay. All right, so this is how you would implement it. Now, what about another way of implementing it? Let us say, is there another way of implementing it if you don't want to use a different deferred correction approach? Yes, you can do it. Essentially, what you have to do is, if you want to do in another way, what we are losing here is the diagonal dominance, right? Your Scarborough would not be satisfied. So you can make it satisfy diagonal dominance or Scarborough by using some kind of relaxation, right? If you have a relaxation factor, you can make it go up, right? You can make it an under relaxation factor or something, and then you can and then you can make it the Scarborough satisfied or diagonal dominance. Okay, so that is another way. But in our particular course, we will use this deferred correction approach because it is much simpler, and also you can write a code for, let's say, the upwind difference scheme and make any other scheme work as well in a very simplified way, because all you have to change is basically the B term, right? Once you change that, you essentially are doing a higher order differencing. Okay. All right. Let us see now how do we, when we concatenate all the equations, let us look at the overall equations. If you have, let's say, a higher order scheme, essentially we are talking about a higher order upwind scheme. Okay, so that means what we have is if you kind of concatenate all the equations, what you get is the discrete equation is AP phi P equals sigma A and B phi and B plus B. Okay, where your A east is, we have already seen this as the diffusion component dE plus max of minus Fe comma 0, and A west equals dW plus max of Fw comma 0. Notice that there is a minus and a plus here. This is because we have defined the flow rate as simply rho u east delta y here, and we have defined it here simply as rho u w delta y. Okay, so we have not defined these as the dot product of rho u bar dot a bar. Okay, rather we have simply written it as the rho density times velocity times area. As a result, we got this minus plus problem, right? Minus plus issue. And similarly, A north would be d north plus max of minus Fn comma 0, and then A south would be d south plus max of F south comma 0. Okay, so this is we have already known about all these things. This is basically your first order upwind difference scheme, right? If you are asked to write code for upwind difference scheme, this is the algorithm. Now, what about the higher order scheme? Essentially, the higher order scheme would contribute to the B term. So as a result, your AP is also the same as before. So if you have AP equals sigma A and B minus the source term, that is SP times delta VP, plus we have F east minus FW plus F north minus FS, right? Essentially, this term is comes into play to counteract the upwind scheme, whether it is going into AP or A east, right? Only for that this is coming into play. And again, we know that the term here in the parenthesis would evaluate to 0 if your underlying flow field, that is the U bar, let's say if it satisfies continuity, right? If it satisfies continuity equation, then the mass flux that is coming in and going out would be balanced. As a result, this parenthesis term would go to 0. All right. What about B term? B term now contains SC times delta Vp, and then we would contain, if Fe is positive, you would get a Fe times, you would get delta phi higher order term evaluated at star value, right? Delta here is because we have phi higher order minus phi upwind, right? And this is evaluated on the east face, and everything is evaluated at the star value, right? Now, why is there a minus here? There is a minus because what your term is basically Fe times phi p, right? Because Fe is positive, then the contribution will go into AP, and so Fe is positive, then this will go into Fe times phi p, but this is being sent to the other side, so you have a minus Fe delta phi higher order, right? But if Fe is negative, then this would turn out to be going into A east, right? Is this correct? Maybe you need to check for the sign here, if is this correct or not. Okay. Then we have plus Fw delta phi higher order on the west, and then minus Fn delta phi higher order star on the north, plus F south delta phi higher order for the south on the star. Okay. So this extra term is basically the only change when compared to the upwind difference scheme. Okay, so this is the only change because we have used the deferred correction strategy. Okay, so as a result, this is the only change. So that means if you write a code for upwind difference scheme, it is very easy to modify it to use any high order scheme using this deferred correction strategy. Okay, all right. Then let us move on to now something different, because up till now we have been only looking at the Cartesian or we have been only looking at the structured Cartesian meshes, right? And then we have seen how to discretize the convection diffusion equation as well as the unsteady convection equation. Okay. Now, what about unstructured non-orthogonal meshes? How do I solve for convection diffusion equation on unstructured non-orthogonal meshes? Okay, so this is something we take up now. All right, so as usual, we have our two cells. Let's say this is the C0 cell and this is the C1 cell, and the vector connecting them would be the xi direction, and the direction along the face would be your eta direction, and we have these two unit vectors, that is E xi and E eta, and we of course have the global coordinates, that is xy and I hat and j hat, and the face normal vector is AF bar. Okay, and in addition we have now because of convection we have some velocity field u bar. Let's say this is the velocity vector that is in the flow field. Okay, and this is known. Okay, now this is known. All right, then how do I now go about calculating convection diffusion in an unstructured mesh like this that is also non-orthogonal? Okay, so that is the question. Our governing equation is the same as before, right? We start off with the general scalar transport equation, that is partial t rho phi plus del bar dot rho u bar phi equals del dot gamma grad phi plus s phi, right? For now we would only work with the just look at the convection diffusion equation. So we will not a steady convection diffusion equation. So as a result we would set the unsteady part to 0, and of course this is something that can be done easily. So you can see how to extend this to the incorporate the unsteady equation, which we have already seen in the context of structured meshes for convection diffusion. Okay, so if I apply now finite volume method to the convection diffusion equation, of course we can write this by getting this term to the right hand side, okay, as gamma grad phi f dot af bar minus rho u bar phi f dot af bar plus st bar times delta v naught equal to 0. Okay, so this is basically you apply integrate it on a finite volume and then convert the volume integrals into surface integrals using Gauss divergence theorem, and then replace the surface integrals with summation. Okay, that's what. And then we already know how to discretize the first term here. This is the diffusion flux gamma grad phi f dot af bar, and we also know how to discretize the s phi bar delta v naught, right? Essentially make a linearize the source, write the s phi bar as sc plus sp phi p. Now only thing that we don't know is this part, that is the convection term, right, which is rho u bar phi f dot af bar. Okay, remember for the structured meshes we have defined for the east face, west face and so on, we have clubbed rho u bar and af bar together. We call that as some kind of flow rate, right, because it is kind of multiplying density times velocity times the area, the scalar area. So this was rho u e delta y, we define it as fe, right, that is the mass flow rate through the east face. Similarly we defined rho u w times delta y as the mass flow rate through the west face. Okay, remember while defining these things we did not consider the area vector direction. Okay, we have only used the area magnitude. Okay, so as a result we got this plus minus in the definition of the upwind schemes, right? That is the consequence of that. Whereas now what I would like to do is I would like to define our flow rate as rho u bar f dot af bar. Okay, so now this takes into account the plus minus automatically depending on the phase we are. Of course af bar is now pointing out of the cell that we have focused on. Okay, so that means ff is the flow rate, which is basically rho u bar f dot af bar. Okay, that means this term can be written as ff times phi f, right, for each of the phases. All right, if we go about the diffusion flux that we have, diffusion term is gamma grad phi f dot af bar is missing here, equals, this basically has two components if it is a non-orthogonal mesh. One was the primary derivative, the other one was the secondary derivative. So the primary derivative was gamma f by delta xi, af dot af by af dot e xi times phi 1 minus phi 0, right? Essentially phi 1 minus phi 0 by delta xi is coming from your partial phi partial xi on the face, plus we had some term which is basically your partial phi by partial eta on the face. This we call it as secondary gradient. Okay, so that is coming from the diffusion on the unstructured non-orthogonal meshes. All right, now just like what we have done in the structured examples, we would like to call this entire coefficient as some df. Okay, remember we have defined something called d east, which was gamma delta y by del xe, So on similar lines, we would like to define this entire coefficient as df. Okay, d sub f, this is d sub f times phi1 minus phi0 plus secondary gradient of f. Okay, this is fine. This is, we already know about the diffusion discretization, so there is nothing new here. What about the convection term? The convection term, if we write, that is rho u bar phi f dot af bar with our definition of rho u bar f dot af as ff, this term evaluates to ff times phi f, right? Now notice the similarity here. This is basically similar to your fe times phi e. Okay, of course, in the definition of fe is different here slightly because it doesn't consider the direction here. Okay. All right. So then we have ff times phi f. Now, can we write the complete discrete equation? Yes, we can write. Essentially, that's basically you go back and substitute for each of these terms and then write the summation on the f. That basically gives you df times phi1 minus phi0 for f. So that means either this is phi1 minus phi0 or phi2 minus phi0 and the corresponding things depending on the which phase we are looking at, plus you have secondary gradient of f minus you have ff times phi f. Right, so this is basically you are coming from the convection flux, plus we have the source term, that is SC plus SP phi 0 times delta V not equal to 0. Okay, so that is the full equation. Now, just like what we have done in the structured mesh case, we now have to apply a particular discretization scheme for our convective term. Right, our convective term is basically phi f, ff times phi f. Now we need some kind of profile assumption or some kind of value for our phi on the face f. Okay, so if we apply, let's say, central difference scheme, we of course recall that in the context of structured meshes we wrote phi little e that was coming in fe, right, in fe phi e. What we wrote was phi e, we have written as phi e plus phi b by 2 in the context of central difference scheme. Now, if I were to apply central difference scheme for unstructured non-orthogonal meshes, I can write this phi f as a using a simple average as phi 0 plus phi 1 by 2, right? Now, this is okay because although there is a difference in the cell sizes, even if the cells are not uniform, we assume that the phi kind of let's say varies linearly or something. So this is a simple average. Of course, this can be improved upon by using the gradients of phi later on. Okay, so anyway, I would make a simple average. This is basically phi f equals phi 0 plus phi 1 by 2. Okay, that means I would substitute phi 0 plus phi 1 by 2 into the phi f value that we have here. Okay, now what happens when we substitute this? What happens is you have minus ff by 2 going into a0, and then you have minus ff by 2 going into a1. Right, now a0 is your p cell here, right? That is your 0 cell. That means minus ff by 2 would become plus ff by 2 when it goes to the right hand side, and you have a minus ff by 2 that is remaining here. Okay, so that's what happens. Now, because the way ff is defined, this will always be a minus here. Because ff already contains the plus minus automatically depending on the area vector. So as a result, we can now substitute for these values and then form the complete discrete equation for central difference scheme when applied to convection diffusion on unstructured non-orthogonal meshes. Okay, so of course we kind of get back to our nice equation, that is AP phi p equals sigma n b phi n b plus b. Now this is where I want you to kind of draw parallels to the structured mesh discretization. So you have to kind of recall what we have done in the structured context, in the context of convection diffusion equation, and see how this makes sense. Okay, otherwise you have to kind of go through this and kind of derive it independently after we have gone through these steps. Okay, so what would be A and B? A and B is basically in the context of structured mesh. This was D east minus FE by 2, right? This was so if you go about here again, this would be DF minus FF by 2, right? That's what we will get for the neighbors, right? So that is your A and B. A and B would be DF minus ff by 2, because this will stay on the left hand side, that is coefficient of phi ones, right? What about AP? AP would be, of course, sum of sigma A and B, sum of all these guys, but remember that this would come with a plus. So as a result, we will have this extra term, right? F east minus F west plus F north minus F south in the context of central difference scheme. That same thing comes here. But again, we don't have plus minus here. So as a result, this will be summation of FF, right? So we would not have that plus minus thingy here, right? Recall that was there in the context of structured meshes. So this A and B would basically we have df minus ff by 2. That is the reason we are getting this. Okay. Then your B term, of course, has the remaining part of the source term, that is SC times delta V naught, plus we have the secondary gradient term as well, right? The secondary gradient term would remain on the left hand side. As a result, it will be a plus a sigma and B secondary gradient for each of the phase that is shared with the neighboring cells. Okay. So that is what we have. Now, similar to the Cartesian mesh case, if ff is greater than 0, right, if this is positive, will this coefficient be always positive? Will this be always positive? No, right, this is not always positive. If ff is positive and ff is greater than 2 times df, right, then essentially this coefficient can be negative, right? And we don't like negative coefficients, because if you use an iterative scheme, then these Carbonaro criteria will not be satisfied and so on. So we don't like this. That means we have to choose ff such that ff by df should be always less than or equal to 2, right? That means only then your A and B's will be positive, right? That means we are again come back to the same condition, that the Self-Peclet number has to be less than 2. This is basically we had a similar restriction in structured meshes also, right? So the same restriction kind of comes back to us even in the context of unstructured non-orthogonal meshes. Okay, so that is exactly how you go about implementing the central difference scheme on these unstructured meshes. All right, now let us see how do we implement the upwind difference scheme. Okay, so the upwind difference scheme, we again recall from the structured mesh case that phi on the face, phi little e, is either phi p or phi capital E, depending on the direction of the mass flow rate, right? If Fe is greater than or equal to 0, then phi little e equal to phi capital P. If Fe is less than 0, then phi little e equals phi capital E, right? We recall this thing. Now, of course, the same condition applies here. Only thing is that now phi f is either phi 0 or phi 1, depending on the direction of the ff. That means if we go back to the diagram that we have drawn, which is a couple of pages here. Okay, so if ff bar is positive, right, essentially you can move this arrow here. So if this is going this way, right, that means it is in the direction of af bar, right? If that is the only way it can be positive. Okay, then what will we take? The phi value on the face, we would like to take it as phi 0. Right, if it is going this way, then we would like to take the phi on the face value equal to phi 1, right? That's what the condition says now. Okay, so if ff is positive, then we would take phi sub f as phi 0, otherwise we would take it as phi 1, right? That's what we have. All right, then of course this is the only thing we have to worry about, right? This is your upwind differencing scheme. So once we have defined this thing, we can essentially assemble the equation, right? Assemble the equation. So the discrete equation is basically AP phi p equals sigma n b phi n b plus b, because we already know how to discretize and assemble all the diffusion equation and everything else, right? Which is basically the same as before. Now, what will be the A and B terms? This will be again, if you draw a parallel to the structured mesh, what we get is A and B equals, you get the dE, that is dF, plus max of minus ff comma 0. Okay. Now this will always be max of minus ff comma 0 for any phase that you consider in the cell, okay, or for any cell, because this is always defined the way with the direction. So this will always have plus max of minus ff comma 0. Okay, so you need to verify this. How will this come up? So you need to look at this and verify. by comparison to the structured mesh case. And AP would have sigma A and B as before minus SP times delta V naught plus we would have all this contribution. Okay, again now this term would be 0 if U bar satisfies continuity equation. Okay. All right. Now B term as usual will have SC times delta V naught plus the secondary gradient of for each of the phases. Okay. So that is a very compact and nice equation. Essentially we got discretized the convection diffusion using the upwind difference scheme on unstructured non-orthogonal meshes. Okay, that is very similar to the structured mesh case. Okay, all right. So far so good. Now essentially we have now looked at not only about implementation issues on higher order schemes, and we have also looked at how do we go about discretizing convection diffusion on unstructured non-orthogonal meshes for both the basic convection schemes, that is basically your central difference scheme and upwind difference scheme. Okay. Now one question that we did not answer basically is, now okay, all this is fine, now how about higher order schemes? Can I extend these higher order schemes that we have learned, that is basically your second order upwind scheme or the quick scheme, to unstructured meshes? Yes, of course we can. This is very regularly used on all the software. So essentially we will look at what about higher order schemes, implementing higher order schemes on unstructured meshes. Okay, so again we look at the diagram here. So we have the C0 cell, C1 cell and the AF bar, and we have the phase and the line joining C0 to the phase centroid, we would like to call it as the vector delta R naught bar. Okay, a bar is missing here, and then of course we have the velocity vector, that is U bar. Okay, so that is what we have. Now how do we do this? Essentially in the context of structured meshes, what we have done is essentially we have used the Taylor series expansion, right? And not only the value of phi p, but also the partial phi by partial x and partial square phi by partial x square. All these things are evaluated using central difference schemes. Let's say if you want to do a quick scheme or something like that. Okay, so now the same thing we have to do, of course, now, but things are not in one direction, right? Because we don't have a particular direction that we can go about, because this is now essentially unstructured, so we don't have a particular direction, but we know that we can use a multidimensional Taylor series expansion. That is basically to obtain the value of phi on the face, we can expand this about phi 0, this is phi 0 plus grad phi 0 bar dot delta R naught plus, essentially we expand with our gradient calculation, and then we have the next term would be del square phi times order of del R naught square, right? So this will require you to calculate second derivative of the phi, right? Just like what we have done, but in multi dimensions. Okay. All right. So depending on, again, if you only include this term, we are back to our upwind difference scheme. If you include even this term, then we are looking essentially at a second order accurate upwind scheme, because this term would evaluate itself to order del R naught square, right? Now, if you of course include this term as well, which require you to have del square phi in all the directions, then you are essentially talking about a third order accurate upwind scheme. Okay, is this clear? Now essentially we are looking at, if you only include the first term, we don't include any of these guys, then this is basically the first order upwind scheme. If you include this, then we are essentially talking about an order delta R naught square. That's basically a second order upwind scheme. And again, if you include this term, then the truncation error would be order del R naught cube. That means this will be a third order accurate scheme. Okay. Now, of course, we have already calculated gradients before in the context of secondary gradients. So that means we already know what is grad phi at the cell centers, right? So if we just include that, we can of course build a second order accurate scheme very easily, right? Because the grad phi is available at every cell. All you need to do is basically use that grad phi and reconstruct the value on the faces. And again, this term of course would go into the B term, right? Like the way we have described, if you want to implement it. So this can be easily done. Okay, so far so good. We essentially discussed how to extend the higher order schemes or second order append scheme to unstructured meshes, right? So that's what we have discussed till now, how to extend this to unstructured meshes, the second order append scheme. Now how about the quick scheme? What do I do? I don't have the second derivatives calculated already, so what should I do about calculating quick scheme on unstructured meshes, because that comes up with order delta x cube. Okay, there are multiple ways of doing this thing. Of course, you don't want to calculate the second derivative here and then include all those terms. So as a result, there is an alternative way that is used in the literature. So that is basically kind of generalizing the existing quick scheme on the structured meshes. So we start off with the quick scheme that we have on the structured mesh. Okay, so recall from our structured mesh implementation, if Fe is greater than or equal to 0, then phi little e equals phi p plus phi east minus phi w by 4 plus phi east plus phi w minus 2 phi p by 8. Okay, so this is the original equation for a quick scheme that we have already developed. This can be also rewritten as the equation here. This is basically phi p plus we have a phi east by 4 and we have phi east upon 8. So 1/8 I am writing it here, so this is phi east upon 8, and then minus 1/8 of phi w, that is basically minus 1/4 here and plus 1/8 here. So this would basically give you minus 1/8, that's what I have written here, and the remaining terms are phi east is remaining 1/4 and phi p has remaining 1/4. Okay, so we just modified this equation to look slightly different in terms of phi p plus 1/4 of phi east minus phi w by 2 plus 1/4 of phi east minus phi p. Okay, all right, if that is the case, we can also rewrite this slightly differently by writing it like this: phi p plus, I would like to get the half here, so this will be 1/2 phi east minus phi w upon multiply with delta x and divide with delta x. So we have 2 delta x into delta x by 2, right? In the denominator it kind of multiplies to 8 and you get back the original value here. Similarly, here I would like to write this as 1/2 times del x by 2, that gives you the 4 value here, and we would like to write it as phi east minus phi p by delta x into delta x by 2. Okay, so basically this is another modification of this one by multiplying each of these terms, the second and third term, with delta x and dividing with the delta x. Okay, now what can you say about this term? This is basically if you are at the p cell. Okay, so we are essentially at this is our west cell, then we have the p, then we have the east, right? That means if we are talking about phi east minus phi w by 2 delta x, this is basically calculating the gradient at the cell p, right? So I can write this of course as partial phi partial x p times delta x by 2 into 1/2 plus, what about phi east minus phi p by delta x? Phi east minus phi p by delta x, this will be basically gradient evaluated at the little east, right? Basically at the east face, right? So that means I can write this as partial phi partial x at the east face times delta x by 2. Now what is this delta x by 2? Delta x is the width of the cell, right? Either this one or this one. Delta x by 2 would be the distance between either p to the face e or between e to the e, right? Something like that. So essentially if you are talking about p, this would be the distance between cell centroid to the face. Okay, fine. Essentially now we have kind of transformed this equation for quick scheme, assuming that f e is greater than 0. You have to redo all this if it is less than 0. Okay, that will be slightly different, into something else in terms of a continuous gradients. Okay, now I have done this thing. Now from here we can kind of generalize this equation such that we can build a unstructured counterpart of this equation. Okay, very easily without going into the second derivatives as we saw before. So how do I now write this? This is basically partial phi partial x at p. In general, this would be, because this is unstructured mesh, I can write this as grad phi evaluated 0. Okay, now if we generalize, this is basically phi p would be phi 0, like to obtain the value on the face, this will be phi 0 plus 1/2 times this would be what? Grad phi evaluated cell p, that is 0, dotted with what is delta x by 2? Delta x by 2 is nothing but delta r naught bar, right? We have just drawn this as basically the distance between the cell centroid to the face centroid. This is delta R naught bar. Okay. So we have generalized this formula. Plus, what is the second one? This is half of partial phi partial x at east is nothing but this is in the context of Cartesian structured meshes. This is basically the partial phi partial x. But if we were to generalize this, this is basically your grad phi evaluated on the face f. So this is basically grad phi f. Okay, dotted with this is again delta R naught. Okay, now very nicely we have got an equation here which is a generalization of the quick scheme to unstructured non-orthogonal meshes. Okay, now only requirement of course is that the gradients that we have computed or we will compute, these two have to be at least second order accurate, right? Only then this entire thing will be third order accurate, and whatever we kind of leave it here would be third order accurate. Okay, so this is the counterpart of the quick scheme for unstructured non-orthogonal meshes. Okay, so only requirement is that evaluate the gradients at the cell centers and the faces to at least second order accuracy, such that this entire terms here will be third order accurate. Okay, now following a similar pattern, you can of course derive other higher order schemes such as the second order upwind scheme or beam warming scheme or Fromm scheme using by generalizing those equations as well into unstructured non-orthogonal meshes. Okay, following a similar algorithm. Okay, so that is about it. Essentially, now we have covered today the unstructured mesh discretization for the convection diffusion, as well as we learned how to extend the higher order upwind schemes to the unstructured non-orthogonal meshes. Okay, so I'm going to stop here. Let me know if you have any questions through email. All right, thank you.